Welcome to the deep dive. Today, we're going deep on gold and platinum.
Oh, yeah.
You probably know them as noble metals, like
Yeah.
jewelry, right?
Yeah.
But did you know they're also essential for all sorts of tech? We're talking smartphones, catalytic converters, you name it.
Yeah, and what we're diving into today goes way beyond like their everyday uses.
Okay.
Get this. New research is uncovering some seriously strange things about gold and platinum at the atomic level,
Oh,
especially how their electrons behave.
I've got the research right here. Noble metal, dark edge fermiology, centrifugal barriers, core hole memory, and the Zeeman-Auger effect. Okay, that title's a mouthful.
Yeah.
But the expert speaker is going to help us unpack it.
I'm happy to.
Yeah.
So let's start with a quick comparison of our two stars of the show.
Okay.
Both gold and platinum are noble metals, and they share the same face-centered cubic crystal structure.
Okay.
But here's the kicker. They differ by a single atomic number.
Okay.
Just one proton difference.
Now, that doesn't seem like a big deal, does it? I mean, on the whole periodic table of elements, one proton, more or less.
And that's where it gets interesting. That tiny difference actually causes huge changes in how their electrons act.
Wow.
And that's what this research is all about. Uncovering those differences and what they mean.
So the research paper mentions something called dark edges.
Right.
That sounds a little ominous, doesn't it? Like we're about to enter a dark and mysterious corner of the periodic table.
Sure.
What are these dark edges?
Yeah.
And should we be worried?
Don't worry. No need for a hazmat suit.
Okay.
Dark, in this context, refers to something scientists observed when they shine X-rays onto gold and platinum.
Okay.
Specifically, they're looking at how the X-rays interact with the electrons in these metals.
Hmm.
Now, when they looked at the data, they saw these areas where the X-ray absorption was weaker, kind of like looking at a dimmer light.
Okay.
And they called these areas dark edges.
Okay, so it's less about being ominous and more about how much of the X-ray is being absorbed. But why are these areas darker or weaker in their absorption?
This is where it gets really fascinating.
Okay.
You see, electrons in an atom can exist at different energy levels, kind of like how a ball can be on different steps of a staircase.
Okay.
The dark edges show us that sometimes the electrons are having trouble jumping to a specific energy level because something is blocking their path.
Oh.
Think of it like trying to roll a ball uphill sometimes. It needs an extra push.
So what's giving these electrons a hard time? What's this invisible barrier they're bumping up against?
That invisible barrier is what physicists call a centrifugal barrier.
Oh.
You see, when an electron tries to move to this particular energy level, which we call the Fess orbital,
Right.
this centrifugal force acts like a quantum bouncer, making it harder for the electron to get in.
So it's like there's a VIP area within the atom, and this centrifugal barrier is the strict doorman deciding who gets in and who has to wait.
Precisely. And this waiting room, caused by the centrifugal barrier, directly translates to those dark edges we're talking about. They're a visual representation of this quantum bottleneck.
That makes so much sense.
Yeah.
But hold on, the research paper doesn't stop there.
It doesn't.
It also mentions something called core hole memory. Now, we're not talking about forgetting where you put your keys, are we?
Not quite. Core hole memory is even more mind-boggling than misplacing your keys.
Okay.
It's the idea that when you excite an atom with an X-ray, it's not just like a flissing event.
Right.
The atom actually retains a sort of memory of that excitation, specifically in a region called the core hole.
Okay, so it's like the atom took a picture of the X-ray hitting it,
Yeah,
and that picture is stored in this core hole.
that's a really good way to think about it. And this isn't just some abstract memory either.
Oh.
It has real consequences for how the atom behaves afterward. You see, after the atom is excited, it releases energy in the form of electrons.
Okay.
And the energy of those electrons directly reflects the memory stored in the core hole.
So the atom's past is actually influencing its present. That's incredible. But how do we even know that the atom is holding on to this information? How can we read this atomic memory?
That's where another fascinating phenomenon comes in, the Zeeman-Auger effect. Without getting too deep into the technical weeds.
Okay.
This effect basically says that the energy of those emitted electrons I mentioned, they change depending on how the atom was initially excited.
Okay.
It's like the atom is telling us, hey, I remember that specific X-ray hit.
That is wild. So it's like hitting a drum with different strengths and then listening to how the sound changes.
Right.
You can tell how hard the drum was struck based on the sound it makes.
Exactly.
And in this case, the researchers are listening to the electrons to understand the atom's past. Did they actually observe this memory effect in their research?
They did. They found that this Core hole memory was directly reflected in the energy distribution of specific Auger electrons emitted from both gold and platinum.
Wow.
And to be extra sure, they combined their experiments with some serious theoretical calculation using things like density functional theory.
I'm guessing that's not something you can do with a pencil and paper. It sounds like they needed some serious computing power for that.
You're absolutely right. They used some cutting-edge experimental techniques at the National Synchrotron Light Source 2,
Okay.
which is a massive facility dedicated to producing super intense X-rays for research.
So they have these giant X-ray machines that are essentially peering into the hearts of atoms.
Right.
And then they're using incredibly complex theories to make sense of what they're seeing.
Right.
That's impressive, but it also seems incredibly niche.
Sure.
Why go to all this trouble to understand these dark edges and core hole memories? What's the bigger picture here? So we've been talking about these dark edges and core hole memories.
Right.
What does this all mean, like, for the average person?
Well, what's fascinating is this research isn't just about some obscure corner of physics.
Okay.
It's about understanding the fundamental building blocks of matter in a way we never have before. Like, imagine for a moment being able to predict and even control the behavior of electrons in materials.
It sounds like we're on the verge of some serious sci-fi stuff here.
Yeah, it's not as far-fetched as it might seem.
Okay.
By delving into these intricate atomic processes, researchers are opening up completely new avenues for manipulating materials at their most fundamental level.
So what kind of real-world applications are we talking about?
Oh, the potential applications are vast.
Okay.
Imagine like more efficient solar cells.
Okay.
Faster and more powerful computers, even entirely new types of materials with properties we can only dream of today.
Ah.
And it all stems from understanding these seemingly insignificant details like dark edges and core hole memories.
It's amazing to think that these tiny particles, electrons, hold the key to unlocking such big technological advancements. This research has given me a whole new perspective on gold and platinum.
Yeah, and that's the beauty of scientific discovery, isn't it?
Yeah.
We often think of gold and platinum as these inert precious metals. But beneath the surface, there's a whole world of complexity waiting to be explored.
It makes you wonder what other secrets are hiding within the atoms of everyday materials. If something as seemingly simple as gold can have such complex behavior, what else are we overlooking? I want to thank you for joining me on this deep dive into the fascinating world of noble metals. It's clear that there's still so much more to discover and uncover, and we've only just scratched the surface. Until next time, keep exploring.